So in this example, we have a ball thrown straight up in the air with an initial velocity of 7.36 meters per second. The acceleration of the ball points downwards and has value of minus 9.81 meters per second squared. And it's traveling for 1.5 seconds, and we see that it goes from a position of 0, gets up, 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 small, 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 back down to 0. So if we were going to draw a picture, the ball starts at 0, goes up in the air, turns around, and comes back down. So that's a picture of what happens with the motion. We know that V0 equals 7.36 meters per second. We know the acceleration is minus 9.81 meters per second squared, and to put in our coordinate system, we know that plus y points up. So there's a picture of all the things that we have. Part A says calculate the velocity for each time shown. So we have our times going up by 0.25 till we get to 1.50. So if we want to calculate the velocity, we can use our equation. V equals V0 plus A times t. So at t equals 0, V equals V0, 7.36 meters per second, plus A minus 9.81 meters per second squared times 0 gives us 7.36 meters per second. We'll put that in our table. 7.36, and meters per second is already in our heading, so we don't need to write in the units. Okay, we can follow along using this equation, but we'll keep plugging in the different times. And if you wanted to, of course, you could just do this on a spreadsheet, make it a little bit faster. 4.91 meters per second, 2.46 meters per second, 0 meters per second, rounds to 0 when we do the calculation, minus 2.45 meters per second, minus 4.90 meters per second, and minus 7.36 meters per second. So there's our velocity at every time shown. Part B says plot the position, velocity, and acceleration versus time graphs. Okay, so you could plot this on Excel if you wanted to. I also provided a little bit of graph paper if you wanted to use some graph paper and plot it. So why don't we go ahead and use the graph paper. Just going to rewrite those values over here. 7.36, 4.91, 2.46, 0, minus 2.45, minus 4.90, minus 7.36. Okay, there's our velocity values. Okay, so plot the position as a function of time. So let's use the first graph. So there's going to be our position y as a function of time. Plot it against t on our horizontal. Let's pick a scale for our graphs here. So let's call this y equals 1 meter. Let's call this y equals 2 meters. Let's call this 0.5 seconds, 1 second, and 1.5 seconds. Okay, so there's our scale. Let's put it in. At 0, our position is 0. At 0.25, our position is 1.53. If you're drawing a graph by hand, you got to guess a little bit. It's around there. 0.5, our position is 2.45. So we're up a little bit higher. At 0.75, our position is 2.76, so we're up about here. And then at 1, we plot our values coming back down. And then that's what our position graph looks like. With this kind of a graph, we know that they're not just discrete points on a graph. It's actually a smooth curve connecting all those points. So that's a look at our position versus time graph. Up here is where we see it turning around, going from moving up to going down. So this right here, where it turns around, is what we call a turning point. You weren't asked for that in the problem, but it's good to think about these things as you go along. So there's a turning point. So that's position as a function of time. We also were asked to graph velocity versus time. So this is velocity as a function of time. Time on our horizontal, this is going to be 0.5. We'll call this 1.0, 1.5. Got our values here. At 0 seconds, we're at 7.36. Let's get a scale on here. Let's call that 3 meters per second, 6 meters per second, and 9 meters per second. So at 0, we're at 7.36. That's about here. Again, it's hard to gauge. You'd get a little more accuracy if you did it on Excel or if you used a ruler or something to measure it out. At 0.25, we're at 4.91. That's about here. at 0.5, we're at 2.46 around here. 0.75, velocity is 0, and then we plot the values as they go negative. Of course, that's -3, that's -6, and at 1.5, we're at -7.36, about here. Okay, again, our velocity changes smoothly, so we can connect those dots. This guy here, that one's a parabola. This guy here, this one's linear. Then the last thing we're asked to plot is the acceleration as a function of time. This guy is going to be even easier. Let's put our time scale on there. And let's put our acceleration scale. I'm going to call this one -5 meters per second squared. I'm going to call that one -10 meters per second squared. The problem says that the acceleration is -9.81 meters per second. So no matter what time it is, the acceleration is the same at -9.81. That's true for all the times. So this one is constant, so it's horizontal. Technically it's linear, but it's a special case of linear where it's horizontal and the slope is equal to 0. Okay, so there's our graphs drawn. The last part says find the slope and the intercept of the velocity versus time graph. We'll do that graphically. Then it asks, what do you notice? So let's do our slope of our velocity versus time graph. So if we're going to do the slope, let's pick 2 points on the graph to do the slope of. You can pick any 2 points we want. I'm going to pick this point. So this point is at 0.75 seconds and 0 meters per second. And I'm going to pick this point. This point is at 0 seconds and 7.36 meters per second. So our slope equals rise over run. Our rise is going to be 0 minus 7.36, that's our change on the vertical, divided by our run, which is 0.75 minus 0, that's our change on the horizontal. Put this through the calculator and we get minus 9.81 meters per second squared. So what we notice is that our slope is equal to the acceleration. Intercept we read off the graph and we see that this line cuts the vertical axis with a value of 7.36. So our intercept equals 7.36 meters per second, equals our initial velocity. So this kind of lines up with what we know about those graphs. The equation for velocity is v equals v0 plus a times t. We could rewrite this, just swap these two terms. V equals a times t plus v0. And this is a straight line graph. So this is a straight line graph. We know that has an equation y equals mx plus b. So if we have a linear graph, y equals mx plus b. What that shows is if we plot y on x, if we plot the velocity on the y-axis, or the vertical, and we plot the time on the horizontal, so the time on the x-axis, then what we get, so v and y are the same, t and x are the same, so slope and acceleration must be the same, and intercept and initial velocity must be the same. And this is a concept that comes over and over in our graphing application. So when we graph things, this is how we sort out what is equal to what. So there's that example worked through.